Yes, now we are recording. Okay, so where we are. Yes. So before we go into the actual thermodynamics, a few words about if we're talking about power plant engineering, what kind of power plants we have in Finland. So we can see from here that hydropower around 20%, wind 10, solar so little that it hardly matters, and basically everything else is some kind of thermodynamic cycle, and that means that the sort of power plant that we are learning to calculate and understand during this course. We're not particularly focusing on nuclear power. The nuclear engineering guys have their own courses on that, but we mentioned the peculiarities of nuclear power production in a couple of times very briefly. But other than that, we are talking about mostly steam power plants and thermodynamics of that, and towards the end of the course, a little bit about gas turbines only also. And now, the rest of the lecture, I'm going to be talking about thermodynamics to the extent that we are going to need it in this course. So basically, if you are energy major student and you have studied thermodynamics recently and it's still in fresh memory, this will be probably a lot of very familiar stuff. But if it's been a while and you have forgotten some of it, then we are going to cover the main concepts. And I'm not trying to teach thermodynamics, so I will cover only those things that we will actually be needing in this course. And I will mostly try to cover it from kind of engineer's point of view. So explaining the theory to the extent that I think it's necessary to understand, but not really go into the real basics. So definitions, terminology, the first and second law, then about the state and state diagrams and thermodynamic cycles. And let's get started with the definitions. So very first thing, what we mean when we talk about system, that's whatever system, power plant, process, or component that we are looking at. Surroundings means the whole rest of the universe, and boundaries, what separates our topic of interest from the rest of the universe. We have different kinds of systems that we have classified. So open system means that energy and matter can move freely between the system and the surroundings. Closed system means that the boundary is closed but not insulated, so it means that matter cannot move, but energy that is not bound to matter can move. So there can be heat transfer. We can poke an axle through the control volume boundary and turn that, and either the system can do work to the surroundings or surroundings can do work to the system. Then adiabatic is the opposite. It means that the boundary is insulated but not closed. So it means that matter can move and energy can move to the extent that it comes with the matter, but perfect insulation, no heat transfer, no shafts poking through the control volume boundary. And then finally, isolated system means that the system is closed and insulated, so it cannot interact in any way with the surroundings. So usually these are not very interesting systems. Then we talk about properties and state. So properties are what define the state of the system. We have broadly two kinds of properties. We have extensive properties. So these are the ones that depend on how much matter we have in the system. So mass, volume, energy. If we have a big system, it fits a lot of energy inside. So the value of extensive property, you can think that it depends on how extensive the system is. And then intensive properties are the opposite. They are independent of the size. So stuff like density or temperature or specific heat, specific enthalpy, specific whatever, basically, because we can always make out of an extensive property an intensive property by dividing it with the size of the system. So it means that, for example, if heat capacity tells us how many joules we need to put in to change temperature by 1 Kelvin, and then specific heat, we divide that by mass, and we get joules per kilogram Kelvin, and that's an intensive property. We can do the same thing with molar properties also. Divide the extensive property value with the number of moles, and then we get the molar volume, for example, out of a volume. But on this course, we are not going to be using molar properties. Basically, I think not even once, but it's good to understand that such thing exists. Then we can talk about homogeneous systems. That of course means just that all intensive properties have the same value everywhere in the system. There are no changes anywhere. A phase is a physically distinct part of the system, something that we can define a boundary for it, and a surface that separates it from the other parts of the system. And the state or the form of the matter is something similar, but not exactly the same. So with state or form of the matter, we mean solid, liquid, gas, or if it's really hot, then plasma. Phase can sometimes be a little bit different. For example, if we have oil and water mixed, they are both liquid, so they are in same form, one form, but two distinct phases. And same thing with metals, for example, they can have several different solid phases, but those are not really relevant within this course. One important thing about the phase is Gibbs phase rule, and why is it important? So basically, what it means is that the number of degrees of freedom, so that means basically how many variable values we need to know to completely fix the state of the substance. We can calculate that from number of components, that's C plus 2 minus P, which is the number of phases. So what that tells us in practice is usually that if we have one pure substance in one single phase, that is going to have 2 degrees of freedom, and that means that we need to know always the values of 2 state variables, whichever they may be, and then the state of the substance is completely fixed, and the value of every other state variable is completely fixed. Usually what that means in our calculations and in the real world is that very often we know temperature and pressure, because they are the ones that are usually relatively straightforward to measure. And then once we know those two, we can get things like enthalpy, specific volume, specific internal energy, whatever it is that we might need. And in those cases, if we happen to have, for example, wet steam in thermodynamic equilibrium, so then we would have 2 phases, but still one pure substance. And that means that our system has only 1 degree of freedom. So if we know temperature, we immediately know the pressure. If we know pressure, that tells us also the temperature. Only thing it doesn't tell us is what's the relative ratios of the liquid and the vapor. We just know exactly in which state both of those phases are going to be. Then we have different kinds of processes. So basically we have terms for those special case processes where one state property doesn't change. So isothermal process, temperature doesn't change. Isobaric, pressure stays constant. Isentropic, entropy is constant. And adiabatic means that there's no heat input, there's no heat loss. Fifth one that rarely you might come across is something called isochoric. So that would mean that there's no volume change, the volume is constant. Then we have cyclic processes, and cyclic processes means that the system undergoes a change that always returns it to the original state and starts another cycle. So our thermodynamic cycles, the power plant thermal cycles that we're going to focus on this course are exactly that kind of processes. We have a few other classifications for systems and processes. So we differentiate between stationary and non-stationary state. And if we say steady state or non-steady state, that means the exact same thing. That means that stationary system state doesn't depend on time. So it doesn't mean that there is no movement. There can be flows, but there will be no net removal or accumulation of energy or mass or anything else in the system. And the opposite is, of course, that there is change, there is accumulation, there is net removal rate. These are not the kinds of systems that we are focusing on this course. So basically, we only study power plants and components in stationary state within this course. Then we have also the classification between reversible processes and irreversible. So reversible process is an ideal process with no losses, and that's a kind of process that does not exist in the real nature. Irreversible process is a process that we cannot return to its original state without leaving changes to surroundings. So basically, we can always return any piece of matter to its original state, but if the process was irreversible, it means that we cannot return it to that state without leaving a change in the surroundings. And all real processes are always irreversible. There are always losses. Then we can get started with the laws of thermodynamics. And before we go into the first law, there's actually something that we call the zeroth law, which is basically just the definition of temperature. So basically it means that when two systems are in different temperature and they interact, then heat is transferred from higher to lower temperature until the same temperature is reached. So we can say that if object A is in thermodynamic equilibrium with object C, and C is in equilibrium with B, then that means A is also in equilibrium with C, and the temperatures of all three objects are the same. We're using two temperature scales here. So sometimes we talk about temperatures in Celsius, sometimes in Kelvin. The delta T is always the same if it's in Celsius or in Kelvin, but Kelvins are 273 degrees higher value than the Celsius. And very often we are dealing with temperature differences, so then it doesn't matter which one you use. Sometimes in an equation you might see that a temperature is divided with something, or something is divided by temperature, or temperature is raised to a power. And that should always tell you that in this equation you have to use absolute temperature or Kelvin degrees. But with temperature differences, it doesn't matter. And then to the first law. So that's the one of the absolutely central concepts in the whole course and all courses in energy department in LUT. So basically it tells us that we cannot make a machine that would create more of some form of energy than it destroys others. And we can't also build a machine that destroys more of some form of energy than it creates others. And this means that if we have an isolated system, then we can change the forms of the energy, but we cannot change the amount of energy. And that basically allows us to draw an energy balance. So draw a balance picture and then write the balance equation. So here we have a very simple system, open flow system in stationary state. And we have a mass flow rate coming in, M1, and mass flow rate going out, M.2, and some amount of heat coming in, Q, some amount of work is being done to the system. So that is going out. And in stationary state, we can say that energy coming in has to be exact same as energy going out. And we can also write another conservation equation for the mass. So we call that sometimes continuity equation, means that mass coming in stationary state has to be mass going out. And then what types of energy are we dealing with? So roughly speaking, we have two kinds of energy, that is bound to matter and that which is not. And energy that is bound to matter includes, for example, mechanical energy. So we have kinetic, potential energy, familiar equations from high school physics probably for most people. So we have the kinetic energy is 0.5 times mass times velocity squared, or we can define it as specific kinetic energy when it is just 0.5 times velocity squared. So we remember that we can always make an intensive property out of an extensive one by dividing it with mass, which is exactly what is being done here. And the same thing with potential energy. So gravitational acceleration times height from a zero level times mass. Then we have internal energy. We mark that with U. So that's the energy of microscopic molecular movement. Includes both translation, rotation, and vibration movement. So it's kind of a microscopic kinetic energy in a way. And then we can theoretically have many different kinds of energies that is bound to matter: chemical energy, nuclear energy, surface tension is rarely significant, but sometimes can be. Those are the types of energies that we don't really concern ourselves with during this course. So mechanical and internal energy is the central concepts of energy bound to matter. But then we have energy that is not bound to matter. So we have work and we have heat. Work we label with W, and important thing to remember is that it includes the work to move matter into the system or out of the system, or to change volume or to change pressure. So we call this sometimes PV work. And then we have heat. And with heat, the important thing to realize is that if we put hot matter into the control volume, it becomes part of the system. We didn't put heat into the system. We put internal energy into the system. Heat is something that moves without matter. So it's the energy that can be transferred through the system control volume boundary. And heat basically only exists at the control volume boundary. And all types of energy, work, heat, and that which is bound to matter, but let's focus first on work and heat a little bit. The dimension is 1 joule. And the work and heat, they were the two kinds of energy for us which can move energy into and out of the system without any flow of matter. And I was already mentioned that there is this what we call PV work. So we always do work when we bring mass into the system or out. Either the surroundings are doing work or the system is doing work. If we compress something, we're doing work. If something expands, then that something is doing work. And if we have any kind of shaft that is crossing across the control volume boundary, and either the system is turning the shaft or something outside of the system is turning the shaft, then work is being done. And heat, so that's once again not bound to matter. It is what we can transfer by conduction, convection, or radiation. And within this course, we are not really talking about heat transfer. We just concern ourselves with the idea that such a thing exists as heat transfer, and it can transfer energy into and out of matter. There are sign rules in the United States. It says that work done by the system is positive. In the EU, the work done into the system is positive. What I would recommend is that don't concern yourselves overly with any sign rules. What I would recommend is always when you start to draw a balance equation for any system, unless it's really simple, really obvious, and you are 101% sure that you can just write out the equation, first thing is to draw the balance drawing. And then mark everything with arrows, and then write the equation according to how you drew the arrow. And keep in mind of what you mean with that arrow always. And that is the best way to get the equations right every time. And then out of work and heat, we get power and thermal power. So basically means energy per unit time. For power, work per unit time, dimension is watt. And for heat rate or thermal power, those things mean the same thing. it's the amount of heat per unit time and also watt. Now we can start looking at the energy balance a little bit more carefully. So it's the same picture as we saw in the beginning, but now we are marking the, instead of having work and amount of heat, we have the heat rate and power coming into the system and going out of the system. And mass flow rate 1 coming in, mass flow rate coming 2 going out. And we remember that if we are in steady state, then mass flow 1 has to be mass flow 2 because there are no others and we cannot have net accumulation or net removal rate. That means basically that with this kind of system, when we neglect all chemical, nuclear, surface tension energies and such, we can say that what is going into the system, the mass flow rate brings with itself its internal energy. So specific internal energy is marked with a lowercase u. Then we have this flow work, what is sometimes called PV work. There's the kinetic energy, and there's the potential energy, depending on what's the level, what's the height from zero level. And the phi is the heat rate, and P is the power that the system is doing. And specific internal energy is a state variable. So basically, once we know temperature and pressure, which are those ones that are usually easy to measure, then we can determine from state diagrams or from formulas what has to be the specific internal energy. Before we go further, we can take a closer look at this flow work or PV work. So pressure times internal volume. And what we often do is we use a term called enthalpy. So basically, if we look at this mass flow 1 that is coming into the system, and we focus at the control volume boundary, and we imagine that there's a pipe going into the system. There's one element of substance that we want to push into the system. So basically, there's some really thin, short distance S that we have to push that element of substance so that it moves from being outside to being entirely inside. Remember from high school physics that basically work is force times the distance. And the force that is pushing in the matter here is, of course, the pressure that is affecting this small element of substance behind it in the pipe. So force is pressure times area of the pipe. And if we look at that, area times the distance is, of course, going to be the volume of that amount of material. And pressure times volume is energy and measured in joules. And we can, because this is always present, we cannot move matter into the system or out of it without doing this PV work. So this PV is always present in mass flow rates, and that means that just out of convenience, we can combine specific internal energy and pressure times volume. So either as internal energy and pressure times volume, or specific internal energy plus pressure times specific internal volume. And then we get either enthalpy or specific enthalpy. And this is just a matter of making the balance equation more easy and convenient, because all of these are state variables, and then we can just, instead of dealing with 3 variables, we deal with 1. And we get a little bit easier and simpler equation. Then we can also make other small adjustments. So we can define something called total enthalpy. So total enthalpy, if enthalpy was specific internal energy plus pressure times specific volume, then we add specific kinetic energy to it, and we have something that we call total enthalpy, or actually total specific enthalpy in this case. And very often we can also say that the potential energy change is negligible. So in the power plant process, for example, because we have a cyclic process, all of the potential energy differences, we have pluses somewhere, minuses somewhere, but by the time the process is through, the net sum of those is going to be 0, so we can just neglect that completely in the power plant. And with that those two simplifications, we get a lot simpler equation that basically has only the mass flow, and now we have also removed the mass flow 1 and mass flow 2, just marking it mass flow because we have steady state system. And then the only thing that the mass flow is bringing in and taking out of the system is the total enthalpy. Basically, within this course, when I'm talking about enthalpy, I always mean specific total enthalpy. And that's just it's a bit of a mouthful to say, so it's much easier to speak about enthalpy all the time, and this is how people usually talk about energy. So it is good to know that what is being said is actually not exactly what is being meant. And there are some components where the velocity of the flow is actually something that really does matter. But the thing is that when you slow down, for example, a high velocity flow of steam in a turbine, when you slow it down, what was part of the velocity and the kinetic energy that related to it, that energy has to go somewhere. So basically, we're not making any mistakes here. We're not violating the first law. So we are just kind of shortening and simplifying the equations. And basically, because enthalpy, we mentioned it a couple of slides ago, it's a state quantity, state property. So if any two variables, state variables are known, state is wholly fixed. And basically the PV, same thing, pressure is a state variable, specific volume is state variable. So as long as two state variables are known, then whole state is fixed and we can determine it, for example, from a state diagram. We can also calculate the value from an equation. So basically the temperature has an effect on internal energy. And we have two different specific heats. So change of specific internal energy is constant volume process specific heat, or isochoric process specific heat times the temperature difference. And then change in enthalpy is specific heat for a constant pressure process times the delta T. And there's a small typo I realized there, that lowercase c in the lower line, that should be Cp, and there's an extra V. One very important thing, so there is no, if you say that something is 0 meters, it has no length. If you say that something has 0 kilograms of weight, that means that there is no matter. Enthalpy is not like that. It has no obvious clear value where it is 0. It's just somewhat arbitrarily said that there is such a thing as reference temperature at which enthalpy is 0. And unfortunately, it's not really very well fixed. What is that reference temperature? So very often it's 0 Celsius, but not necessarily always. It can be 15 Celsius, 25 Celsius, sometimes it's 0 Kelvin. So what that means is that whenever you are reading enthalpy values from a diagram or from a table or wherever, always take all enthalpy values from the same source, because otherwise there's a potential to make mistakes, and potentially actually quite big mistakes. So the real, like the value of the enthalpy is the specific heat in isobaric process times the temperature difference between the temperature of the substance and reference temperature, whatever the reference temperature is. And then in addition to conservation of energy, we have some other conservation laws. So mass conservation that was mentioned, it's the continuity equation, but there could theoretically be also in some courses in LUT, momentum conservation might be important. Electric charge conservation is another thing, and there's actually a countless list. But within this course, what we are dealing with is two things: conservation of energy and conservation of mass. And applying those imbalance equations is one of the really central concepts that you have to be good at applying in order to pass this course. Then we get to the second law, and we introduce another state property called entropy. So entropy is basically something that we use to describe the nature and the direction of processes, and there is no physical manifestation in nature for what really is entropy, so entirely theoretical property. And we have a couple of different expressions for the second law. We can state it that heat never transfers from cold to hot. We can say that no real process can be fully reversed to its original state. All systems and processes are irreversible. Or we can say that the process is taking place in an isolated system, the exergy stays constant or increases. And there's, by the way, a mistake that it should say entropy stays constant. That is actually a big mistake. So basically, exergy as a term, it means the energy that the second law allows to be utilized in some useful manner. And the rest of the energy we call anergy. So that is something that we cannot utilize. So if we have an isolated system, we can have processes that destroy exergy. So in reversible process, exergy and entropy stay constant. In a real process, in an isolated system, exergy is destroyed and entropy is generated. And finally, one important definition of the entropy, we're going to find this quite useful towards the end of this lecture. And this is basically, without going into the details, where we get this. And probably, if you have studied thermodynamics, then you're familiar with the TDS equations. But for now, if we concern ourselves with a process where there is only heat transferred to the substance, then entropy change is defined as the amount of heat inserted divided by temperature. And now here we see that we divide with the temperature, so that's an immediate obvious clue that temperature has to be in absolute temperature, so in kelvins. And the unit of specific entropy is kilojoules or joules per kilogram Kelvin, so we notice that it's the same dimension as specific heat. And now we have covered the basic terminology that we need. We have covered the first and second law and mentioned what was the so-called zeroth law, and then a couple of slides about the state of substance and using state diagrams and state equations. So water vapor, TS and HS diagrams are something that we use for calculating and understanding steam power plants quite a bit. And wet steam is what we call a mixture of saturated liquid and saturated vapor. And we have that usually at turbine exhaust, for example, in a power plant. And we can obtain it from the weighted sums of saturated liquid and saturated vapor properties. So if we want wet steam enthalpy, we have a variable x, which we call steam quality. That's the ratio of saturated vapor divided by the total wet steam mixture mass. And that means that 1 minus x is the amount of liquid, so the ratio of liquid to the total wet steam mixture, and then a weighted sum of the vapor phase and the liquid phase of saturated liquid enthalpy and saturated vapor enthalpy is our wet steam enthalpy. We always mark saturated liquid with 1 little dot and saturated vapor with 2. So it's easy to remember that vapor has higher volume, so it needs 2 of those. And that's the symbology that is commonly used, for example, in the water vapor HS diagrams, which I hope most of you have. And if you don't, unfortunately, I think the only solutions are going to be trying to find a good quality image from the internet or using the XTeam that I will try to, during today, upload to the Moodle page. Then let's take a look at the TS diagram. So this is a water vapor TS diagram. And we should be able to recognize what it shows us. So there's basically the thick line is the saturated line. Blue part is saturated liquid, red part is saturated steam. And we notice that there are those within this hill, there are those X constant lines from 0.1 to 0.9. So those are the steam quality that was mentioned in the previous slide. And this top of the hill is a point where temperature is 647 Kelvin and pressure is 22.1 megapascals, so 221 bars. And that's the critical point. So that means the highest pressure at which we can still separate. Well, actually at that point, that is the first point where we can no longer precisely separate liquid and vapor phase. So there is no more boiling, there is just increasingly smooth change of phase from liquid to vapor by reducing volume when we bring more heat to the material. And of course, then we call wet steam everything that is between those saturated lines. And superheated steam is when we have saturated steam and we bring more heat to it, and it doesn't boil anymore, but it starts to get hotter. And supercritical fluid is that amount of fluid that is at higher pressure than the critical point. And then what we call subcooled liquid, it's really hard to actually see it at all in a properly drawn TS diagram. So this is very much zoomed part. This is quite accurately showing the scale. So basically, supercritical liquid, this small dotted line quite close to the saturated line, that's the critical pressure line, and only this very, very narrow band, very close to the saturated liquid line, that includes all of the subcooled liquid. So basically, if we move to higher pressure at constant temperature in liquid, nothing very much happens in the TS diagram. So when we will in the future see this steam cycle power plant diagrams drawn in TS chart, we usually exaggerate massively everything that is happening in that area, just to make it a little bit clearer to understand what is really happening there. For example, when we are pumping something, increasing the pressure of liquid, so we are in this really, really narrow area to the left of the saturated liquid line. So it doesn't mean that the things that happen there are insignificant, but it does mean that the changes are not really that big. And that's actually, we will see later on that this thing is something very important for how the steam power plant really works and functions. But this diagram is very useful for understanding the efficiency of any kind of heat engine or thermodynamic cycle. We will see that in the last couple of slides of this lecture. And yeah, there was the saturated liquid line. Then we can take a look at the HS chart. So basically, same things are drawn here. You can see the constant temperature lines in the light red. Dark red line is the saturated liquid, and now we see that the critical point is no longer at the hilltop, but it's way down on the left side. And in the HS drawing, usually where it's most useful for us is in understanding what happens in the turbine. And that, of course, happens in the superheated steam range, around the saturated vapor, and a little bit into the wet steam range, but not very deep. So usually the HS drawings are for steam and they are for the top right corner. But other than that, just the same areas are here. So wet steam, superheated steam, saturated, liquid, and vapor. Well, most of this course we are dealing with steam power plants, and then the one rule is that we should never ever treat steam as any kind of ideal gas. That's very inaccurate. With ideal gas assumption, we make the assumption that the gas consists of small molecules. They are sparse in the volume, and they only interact when they collide. So this is a fairly accurate assumption and approximation when we are dealing with high temperatures, small pressures. So that means gas that is far from condensation. But with steam power plants, we never really get that far from condensation. So never use ideal gas equation for steam calculations. But when we can use ideal gas, so with flue gases, air, with gas turbines, everything that is going on in the boiler of a steam power plant, we can write that the PV is RT, which is the most convenient form of the equation for us usually. And that basically means exactly the same thing as the ideal gas state of equation that most people probably learned in high school, which is the pressure times volume, not specific volume, times amount of moles times universal gas constant times the absolute temperature. So basically the R on the left side version of the equation, that's what we call specific gas constant. So a gas constant for that particular gas. And we define it as either universal gas constant divided by the molar mass, and it comes out as exactly the same value as the difference between specific volume and specific pressure, specific heats. So, did I say that correctly? So, specific gas constant is the difference between constant pressure and constant volume specific heats. And why it comes out like that is not really something that we need to concern ourselves with in this course. It's just what we need to know that that is how it is. So the left form of the equation, PV is RT, is the important form for us when we need to use ideal gas equation. And internal energy in an ideal gas is a function of temperature alone. So that's a simplification from the general Gibbs rule, phase rule. So as long as we know temperature, we basically have enough information if it's an ideal gas. And the specific heats, whether it's constant volume or constant pressure process, it's actually not, that would be, if it were constant, we would call that gas a fully ideal gas. Unfortunately, gases cannot usually be approximated as such if there's any significant amount of temperature change there. So these specific heats are a function of temperature in a significant way that has to be taken into account. But that is something that we will get into in the second last lecture of the course when we talk about gas turbines. And if we're dealing with an ideal gas mixture, then if there are ideal gases, both gases behave as if the other components didn't exist. So for example, if we have two components, we can write ideal gas equations of state separately for both of the components. And I can see that again, I have a typing errors there. So on the left side equation is correct, but the right side should have subscripts 2 for everything. So I will fix that before I upload the slides. Then we have the Dalton's law of partial pressure. So basically, total pressure is sum of partial pressures of all of the components. Then we can go to the final, last but definitely not least part of the lecture, so introduction to thermodynamic cycles. So we will talk about two temperature heat engines. How do we define thermodynamic cycle efficiency? And this is the point where the entropy concept and definition equation will become useful for us. And then we will introduce what are two very important thermodynamic cycles, Carnot and Rankine. So first off, the two temperature heat engine. So we consider a heat engine that works between a hot source and a cold sink, and we can define its efficiency because energy can only, according to first law, change form, but it cannot be created, it cannot be destroyed. So efficiency, that's a lowercase Greek eta, is defined as the amount of work that is done per amount of heat energy Q brought in to the engine. And according to first law, the amount of work that is being done has to be the difference between heat brought in and heat rejected into the cold sink. And from that equation, we can basically write that in many different forms. So we can divide by QA, the heat that we take from the hot source, and we get 1 minus QB divided by QA. We can define it with specific heats, or we can define it with heat rates, and form stays the same. And then we're getting to why the TS chart was so important and why we were interested in the definition of entropy in case where heat is brought or taken away from substance. So basically, according to that equation, Q can be defined if we separate the variables and integrate. Q is definite integral from starting point to end point TdS, or same thing with specific variables, so everything divided by mass. And what this means is that basically what is heat is area in TS diagram. So if we look at this completely imaginary cyclic process in the TS chart, when we start bringing heat from where the red arrow begins, and again, I know there's a mistake in the slide, so this is from another slide that was in Finnish, and I forgot to translate some of the terms, but I will explain it in English, and hopefully everyone will understand. So basically, the red arrow means the state of the substance as heat is being brought in. And heat addition begins at the beginning of the red arrow, of course. And then from the definition of entropy and from the integral equation that we got for it, that of course means that graphically we can depict the amount of heat brought in as the area in TS chart that is underneath the curve of heat addition. So that's the pink area there. And then when we are removing heat from the substance, we are moving from right to the left. And again, the amount of heat that we remove is the area below the heat removal arrow. And that's the dashed part of the TS chart. And that means that specific work done by this kind of process is everything that is between these two arrows. And Carnot cycle is a specific case of this cycle because from now we can understand that basically, if we go back just a little bit, so basically, if work is the area that is between these two arrows depicting the heat insertion and heat removal, that means that the fatter we can get in vertical direction, this cyclic process, the better our efficiency is going to be, because that means that we are getting more net work out of our process relative to the heat that we are putting in. And from this we can also realize that basically if we have certain temperature levels, heat source and heat sink, then the highest possible efficiency that we can get out of such thermodynamic cycle is when the entire heat addition takes place at the constant temperature, which is the temperature of the heat source. So again, the temperature that is shown in this drawing is the temperature and the state point of the work fluid in our thermodynamic cycle. And there, in the real world, there's always going to be a temperature difference. That's a requirement for having heat transfer. But the upper theoretical limit that how good it can work is that our temperature of our substance would remain constant at the temperature of heat source in heat addition and constant at the temperature of the heat sink in heat rejection phase. And then, because this is a fully ideal process, that we assume that from point 2 to point 3, we are isentropically expanding the temperature Tb. And then from point 4 to point 1, we are isentropically returning the temperature of Ta. So basically, if you remember how the constant pressure charts, constant pressure curves were in the Ts chart. So that means that when we go from 2 to 3, we have to go to lower pressure. And when we isentropically increase the temperature from 4 to 1, it means that we are also increasing the pressure. So 4 to 1 is compression and 2 to 3 has to be expansion. And we can write a so-called Carnot efficiency for this kind of Carnot cycle, where heat input and out rejection are constant temperature, and between those are isentropic expansion and compression. So Carnot efficiency is the highest theoretical efficiency that we can have for a thermodynamic cycle operating between two temperature levels. And efficiency, as we defined, that's the specific work done per heat input. Specific work is the difference between heat input, heat output. We can divide by heat input to get 1 minus ratio of heats. And by the definition of entropy, we can write the heat input, heat output as absolute temperature. Again, we are multiplying something with temperature, so it has to be kelvins, times the entropy change, delta S. And that means that our definition of Carnot efficiency between two temperatures is 1 minus the ratio of temperature of heat rejection to the temperature of heat input. And again, has to be kelvins because we are dividing. And that means that the higher the temperature of heat input, the better our efficiency. The lower the temperature of heat rejection, the better our efficiency. And this is a central concept. So basically, when we are in the future talking about how to improve the efficiency of any kind of power plant, we are always first and foremost interested in how to improve the average temperature of heat addition. And secondarily, we are interested in how to reduce the temperature of heat rejection. And Carnot efficiency is what tells us the theoretical upper limit of how high we can get the efficiency. And then the final couple of slides of the course, what we're going to cover today. So this is the Rankine cycle process. This is the ideal comparison process for a steam power plant. So we have a drawing of what would be the simplest possible steam cycle power plant. Then we have an ideal version of that kind of power plant drawn in the TS chart, and the same thing in the HS chart. And bright red means superheated steam. Dark blue means subcooled liquid. So that means that we are in TS chart to the left of the saturated liquid line. And in between here, we have the wet steam mixture. So here we are boiling because we are moving this direction, and here we are condensing in the condenser. And because this is an ideal comparison process, so if we start to look at what happens, for example, from point 1 when we enter the turbine. So we have isentropic expansion in the turbine. We are coming down in TS chart vertically straight down. Isentropic means entropy is constant, and that means that it's reversible process, and imaginary process doesn't happen in the real world. Same thing in HS chart, we're coming down in a straight line in the S. Then in the condenser, we're having isobaric, and if it's isobaric, it's automatically also isothermal condensation in the condenser, and we come out of the condenser as saturated liquid. So there's actually very good approximation to what happens in the real condenser. We have subcooling, it's completely unavoidable, but it's so little usually that we can normally consider it negligible. And within this course, unless we explicitly state something else, in a condensing power plant condenser, we can assume that subcooling doesn't take place. Then we head to point 3, and following that is point 4, and between is the feed water pump. And again, ideal comparison process, so feed water pump works isentropically. Now in this TS chart in the middle, we have drawn it that the point 3 and point 4 are quite distinctly separate, small relative to the turbine, but still distinctly separate. And we remember that if we would draw this as it happens in a real TS diagram, we wouldn't, on such small drawing, be able to separate 3 and 4 at all. And then we start to bring heat. So basically, in this drawing on the left side, boiler is where we bring heat. And what happens there, we can divide into 3 different states. Every one of those in an ideal process is considered to be isobaric, so no pressure drops, constant pressure. First, we heat this subcooled liquid. So if we started from point 3 as saturated liquid, we increase the pressure, so it becomes subcooled. We are a little bit off to the left side from the saturated line. When we start to bring heat, we can heat it quite a bit before we reach the boiling point at that pressure. And that boiling point is at 0.5, and there is again this light blue dot, which signifies that at that point we are at saturated line. We keep bringing more heat. It means that the temperature doesn't change, but we are moving the work fluid from liquid phase to the gas phase, and then we are in this really dark red dot, saturated vapor. And when we keep bringing in more heat, the bright red superheated steam temperature begins to increase, and we move further and further away to the superheated region. And finally, as the very last thing, turbine was mentioned a couple of times, and this is going to be basically the first little touch to the real world and losses in a power plant. So, and yet again, I noticed that there is some Finnish that I forgot to translate this to headline, but basically what it should say there is isentropic expansion efficiency. So we basically define how good our actual real world power plant turbine is with isentropic expansion efficiency. And the turbine is where the gas or the steam does work. And now our ideal comparison process and how it works in the Rankine cycle, which was the ideal comparison for a real power plant. It's isentropic expansion, so we start from point 1 and we come down with constant S as a straight line to whatever is our condenser pressure, P2. And the real world process has losses. That means that we are increasing entropy and we are destroying exergy, and we move to the right on the TS chart. And that means that we cannot get quite as low. So in the TS chart and in the HS chart, in both, it looks kind of the same. And it means that we cannot get to quite as low temperature and quite as low enthalpy as we could in the case of a fully ideal reversible isentropic expansion. And basically we define the ratio of the real enthalpy change and the ideal process isentropic enthalpy change as H1 minus H2 for the real and H1 minus H2S. So 2S is how we mark the endpoint of the isentropic expansion. And as we usually define the efficiency is how much we get out for real divided by how much we would get out in some ideal lossless process, which in this case is the isentropic expansion. So this in its simplicity is the definition of isentropic efficiency, and how we use this is basically that and there will be some calculation examples that I will open in the Moodle page in the next couple of hours. I still need to check that translations are correct. Hopefully there are not many mistakes like we had a few in this lecture. But basically, we usually know at what point steam enters the turbine. We usually know at what pressure our condenser is, so we know where, on what isobaric constant pressure curve our expansion ends. And that means that we can very easily define where is our endpoint 2S. So we have point 1, we have point 2, and then when we know what is the isentropic expansion efficiency of our turbine, from this equation, the only unknown remaining is the real endpoint, and we can solve that. So there's an example of how to apply this in the example calculations that will be open in Moodle in a couple of hours. And this is one of the things that some of the quiz calculation questions might be asking. So basically this was the content of this lecture. I hope this cleared, and I will once more underline that anything that came in this lecture that felt that you didn't completely understand, it's really important to try to study that now and make sure you understand completely what is going on. Same thing for the next lecture, and then the other remaining 4 lectures is a lot of applications of what we learned in the first 2 lectures. So do put in enough work right in the beginning. That's going to save you a lot of trouble in this course towards the end. At this point, does anybody have any questions?
Hello.
Yeah.
By the way, I don't know if anyone has asked about this, but do you know like where can we get this TS diagram? Because I think if I remember correctly in Aleph, there's only HS diagram. I'm not sure though.
Yeah, so HS diagram is what we use to get precise values and where you really need to be able to read exact values. And the TS diagram is something that we are quite happy with just a hand-drawn diagram or the diagrams that you could find in this lecture, for example. So TS diagram, we don't need to get precise values from. We use HS for that, and TS is where we kind of try to understand what's going on.
Oh, so there's no need. So okay,
You don't need a TS diagram that is precisely drawn.
Okay.
Anything else?
This lecture was worth 3 thermodynamics lectures at least.
Okay, that is good to know.
So thank you.
You're welcome. Okay, silence at this point, so I guess no other questions. So good luck for the quiz. I will open it today once I have all the materials open, and then you will have 1 week to answer it until next week. Thank you for the attention.
Thank you.